Hello everyone! Today we'll talk about the problem trapping rainwater. The statement is short, so let's read it. We're given n non-negative integers representing an elevation map, where the width of each bar is 1, and we have to compute how much water it can trap after raining. We're given a nice drawing. Those black squares are mountains, and those blue squares are squares where water is trapped between two mountain peaks. It cannot run off to the left, cannot run off to the right. And we have to calculate the number of those possible blue squares. Today I will talk about two solutions to this problem. And the first solution, which I think is more intuitive, is essentially exactly what I just said. So let's copy this nice image over. And let's think about all those blue squares. Now, when you have a blue square, then it can be blue exactly because if we look at the peaks to the right and to the left, we can encounter a peak that is at greater height, well, in this case, greater or equal height as this square. So, for example, for this one, we see that indeed this one is blocking it, and this one is blocking it. What's more, since in order to have a high black square, we have to have black squares below it as well, then we might as well just assume that the highest black square in a given spot is what's blocking us. So for instance, for this blue square, we might as well just say that this one is blocking us and this one is blocking us. So essentially what we have here is that we look to the left and to the right, we see the highest elevation we can see there. And if that elevation isn't high enough, we know that, well, water here will run off to that side. And if both of those are high enough, then water will be trapped. So, in order to solve this problem this way, we just have to be able to say what's the maximum to the left, what's the maximum to the right. The answer would be the minimum of those two values minus the current height, sum over all x coordinates. That's our answer. And it's very easy to be able to answer those queries about maximum on the left, maximum on the right. Probably the simplest one is just to explicitly calculate at least one of the two arrays of cumulative, right? So for instance, prefix maxima. So essentially, in this example, what we would have would be 0, 1, 1, 2, 2, so on, here 3, and 3 goes on to the end. So those would be prefix maxima. And so, since at this position the answer is 2, then indeed this is height 2, that's to the left of this position. Here the answer is 3, and indeed here we have a 3. And then going backwards, we can either do the same thing, or even simpler, just use the normal algorithm for finding the maximum. So we just remember the one number, 1, 2, 2, so on 3, and now we remember the 3. So we only change that number when we see a greater maximum. Okay, so let's see this version implemented. There's nothing special about it. We just remember the prefix maxima in a standard way, so those are just the cumulative max. And then we go backwards from the right, remembering the current suffix maximum. And at every point, our result would be the minimum of those two minus our current height. And sum over all this is our result. Okay, so this algorithm is, of course, works in linear time. But it also requires linear space. There is, however, a bit more of a magical algorithm that, of course, still is linear because we cannot go better than that, but it uses constant space. So let's talk about it now. Oh, and by the way, of course, those prefix maxima can also be maintained as a monotonic stack. But in general, that would also be a linear space, so that's not an asymptotic improvement for us. Okay, so let's again copy our image. And now we'll think about a different, more clever solution. The basic idea is perhaps a bit similar. We'll still be remembering the prefix maximum, we'll be remembering a suffix maximum, but we'll not be going just one by one over the x coordinates. Instead, we'll be going from the left and we'll be going from the right. And the central observation that will allow us to solve this problem in constant space is that if we remember the prefix maximum up to our left position, the suffix maximum up to our right position, then one of those is at least as great, at least as big as the other. And that means that, let's say, without loss of generality, that the right maximum is greater than the left maximum or equal, then if we've calculated prefix maxima up to a certain position and we are looking at the next position to it, then certainly the maximum to the left is what we've calculated. Because we've been going through the left and this is the next spot, so there is nothing that we skipped. And we don't know the maximum to the right, but we know that the maximum to the right is at least what we've seen up to the right pointer. And since this is at least as big as the minimum we've seen on the left, then we might as well just assume that, well, this is okay, this could be the maximum. Since we are not limited from the right, we're limited from the left, right? Because the left one can be too small. And by doing that, we know that whenever with one of those two pointers, we take the one that's smallest, or if they're equal, then it doesn't matter which one we take, and we look at the next step, so perhaps now at this position, then we can update the result by pushing this pointer one step in its direction. And of course, when the two pointers meet, then we've calculated the sum over all the positions. In other words, instead of calculating the prefix maximum, suffix maximum, we'll be calculating a lower bound of those maxima. That lower bound would be the previous, right? So if we're interested in this position, then if we know that the suffix maximum here is 2, and we know that the prefix maximum up to this point is also 2, then we don't have to know about this 3, since this 2 is good enough. And that technique allows us to solve this problem in constant space. So let's see the code. So here above, we have a version where we remember the left and right maxima, starting with 0. And we also remember the current index that we're looking at. And until those indices meet, we decide which one to push, depending on which one is smaller. So for instance, in this case, we push the left one, since the right one is the right maximum is at least as big as the left maximum. And in that case, we know that we're being limited from the left. The amount of water that we can put at this position is, so the left maximum minus the current height. And of course, we update the left maximum, because if we now see a greater height, then suddenly we might be able to start pushing the right pointer. And of course, for the right pointer, that's the same thing. Since if we're pushing it, then we're limited from the right. We add this to the result. And of course, at the end, we return the sum of all those numbers. By the way, here we are comparing the elements at those indices, and not those prefix maxima and suffix maximum. But we could be also comparing them, since if the height of the left index, for instance, cannot be greater than the maximum from the left, it can be smaller, but if it's smaller, that means that the maximum from the left was smaller, and that's why we're pushing the left pointer. And so at least one of those would always be the one of those maxima, and the other one cannot be greater than its corresponding maximum. So we could just compare here LV and RV. However, by writing it like this, we can also notice another thing, that by doing it in a proper order, the order of operations of updating the values, we actually don't have to remember both the left and right maximum. We can only remember the single value, which is limiting us both from left and right. And this is the solution that's below. So if you want to compare those two solutions and try to understand why both of them solve this problem, of course, it's a nice exercise to the watcher.